Here we have question 1. It says an electron and a proton are accelerated from the rest through a potential difference of the same magnitude. After acceleration, the speed of the electron is VE and the speed of the proton is VP. Which of the following is the best estimate for the ratio VP is to VE? So obviously we are going to be using this formula over here. The VE will be the work done that was being done on the proton and the electron, and that will give rise to the rise in kinetic energy, and from that we can work out our V squared. Now, because they are both electron and proton have got the same charge, E, and they went through the same potential difference, they'll both be given the same amount of energy. So the kinetic energy for both of them will be the same. But because the one has got a greater mass than the other, the velocities won't be the same. So we're going to have Vp as to Ve. That's what we want to find out. Now we know that Ve for both of them is the same, and that's equal to a half mass of the proton, velocity of the proton squared, divided by a half mass of the electron, velocity of the electron squared. Now, because these are equal, that's going to equal 1, and we'll have a half and a half. So we'll get our Vp as to Ve. We're going to just cross multiply here, so we have mass of the electron over mass of the proton, and because we've got squares here in both, we have to take the square root like that. Now the mass of the electron is of the order of 9 times 10 to the negative 31. I'm rounding this down because we can see that this is just an estimate, and the mass of the proton is about 2. It's about 1.7, but I'll do it as 2 times 10 to the negative 27. And when we take the square root of that, that's going to be Vp over Ve. We're going to get something like 1 over 1,800. And if we do that to one significant figure, we will get this. So our answer is going to be C. Then on to question 2. We have a long straight wire carrying a current carrying wire is placed normal to the plane of the page. The current in the wire is into the plane of the page. So that's why we have the cross there. That shows that the current is going in. Which of the following diagrams best represents the magnetic field? Now we use, to find the direction of the magnetic field, we use for our right hand, we use the thumb in the direction of the current and the curled fingers in the direction of the magnetic field. So when we do that, we see that we have got a clockwise, so we could either be C or D. But D would be the better answer, because here, as you move away from the wire, your magnetic field will actually decrease, and the number of lines, magnetic field lines per unit area, gives an indication of the strength of the magnetic field. So D would be better, because here it's showing that your magnetic field is decreasing as you're going from the wire, where here, where they are evenly spaced, it's a constant, or it's a uniform magnetic field, which isn't the case. So C is not the correct one, D is the correct one. Question 3. A direct current DC motor is connected to a battery by means of 2 leads. What is the function of the commutator of the motor? Now, the commutator, as can be seen, is what is linked to the wires to cause a reverse in the direction of the current in the coil of the motor. So as it swings over, the current reverses, and so it can maintain its rotation. So it's D for that one. If you want further explanation on that, I'll be happy to help you with that. Question 4. We have the diagram below shows two long parallel wires. Magnetic field strength at point P due to wire 1 alone is B0. The magnitude of the magnetic field strength at point P due to both wires is. Alright, so we have a look at those. So I'm going to just see if I can draw a diagram just to help explain that. I'm going to draw sort of like a circle in 2 dimensions. So that's for the one wire. That's the magnetic field, and this is for the other one. Like this, just imagine that's a circle. Now, if I put my thumb in the direction there of my right hand, you can see that the magnetic field will be like this and be going into the page there. And for this one, it's going up again, so it will be like this, that direction, and like that. And therefore again we're going to be having a cancelling out in between. So because they both got the same current and this is equidistant, we would expect that they'll cancel out and we should have zero magnetic field there, so it would be A. Question 5. We have a positively charged particle enters a uniform magnetic field. The direction of the particle's velocity is parallel to the direction of the magnetic field as shown in the diagram below. So I'm going to need this formula down here. We're going to use this formula over here. This is the force with a charged particle going through a magnetic field, and this sine theta is the angle between the magnetic field and the direction of the charged particle. In this case you can see they are parallel to each other, so this is going to be 0. So this sine theta will actually be 0, and therefore the force is equal to 0. So there's no force going to be applied to this charged particle, so it would just continue straight like that. Question 6, a similar sort of question. We have a straight conductor is in the plane of a uniform magnetic field as shown. The current in the conductor is I, and the conductor is an angle theta to the magnetic field. The force per unit length on the conductor due to the current in the magnetic field is P. Which is the correct expression for the magnitude of the magnetic field strength? Now, because we've got a conductor in a magnetic field, we're dealing with this formula over here. I have got F, force per unit length, would equal Bi sine of theta, and this force per unit length is given as P. It's given us, so we have P is equal to the strength of the magnetic field times the current times the sine of theta. So we want B for the magnetic field, so obviously we're going to divide through by that, so it's going to be P over I sine theta, so it will be C. It will be the correct answer. Question 7, similar to another one we had before. The function of the split ring commutator in a simple direct current DC motor is to reverse the current direction of the current, and we can see it's the reason for this in the coil, so to control the speed. It doesn't really control the speed, although it will have an influence, I suppose, overall of the speed. In the coil, so the coil will rotate continuously. This is correct. And it is in the coil. It's not in the external circuit, but it's actually in the coil between the magnetic field. So it's going to be B. This is correct.